Okay, so today we're going to begin chapter 6 and we'll finish it up on Monday. I had hoped to try and create a lesson that would encapsulate it all, but I wasn't quite able to do that. And so on Monday we'll finish it up, and then next Wednesday will be somewhat of a bonus lecture. And so either one of two things will happen. Either I'll go over an advanced proof so that those interested can have an introduction into something along those lines, or I will go into reviewing the structure of an advanced project. And so I've been working on one that I intend to check into GitHub, and if we go that route, then I'll review the different components of it. We'll go over the construction of the UI, what it looks like, the HTML, a little bit of the CSS. We'll go over that lightly because really it's something that can really only be grasped through practice and repetition. So anyone interested in that will have to find a project and sample projects and go over that on their own. The construction of the database, some of the syntax there. For the project I'm using PostgreSQL, which is a variant of one of the many available SQL languages. It's procedural language SQL. Postgres is a database that's freely available, but the syntax is similar to what you might run into if you use an Oracle database. The other T-SQL, transact SQL, is used by MySQL and Microsoft SQL Server and MariaDB, which is an offshoot of that. And so you'll either typically run into either T-SQL or PostgreSQL when dealing with databases. But we'll go over briefly how to create the data there, and then we'll look at what the project structure is with a C# backend API. And we'll talk about the different layers of an interior architecture, and then also briefly discuss how it would be deployed in a production environment. So one of the two, either an advanced project or an advanced proof. And that's all assuming that I'm able to finish up chapter 6 on advanced counting. And so yeah, let's jump into it. Actually, advanced counting, I think, is actually a different chapter in the book, but this is the basics of counting. Okay, and so there's 4 basic rules, which I've broken down into 3 because I didn't consider the division rule all that interesting. There's the product rule, the sum rule, and the subtraction rule. And then we'll do combinations and permutations and the pigeonhole principle next Monday. Okay, so the product rule basically says that if you can do something in 2 ways, and we label them in 1 and in 2. Then the number of ways that you can do both of them, the AND operation, and earlier in the semester we discussed that AND is equivalent to product or is equivalent to addition, right? So this follows from that line of thinking. And so if you can do the first one in 1 ways and the second one in 2 ways, then the number of ways you can do them both is in 1 times in 2. And so the example that I pulled from the book is selection without replacement. And so it says a company with just 2 employees, Sanchez and Patel, rents a floor of a building with 12 offices. And so you need to imagine 2 people trying to decide who gets which office. And so they play paper, rock, scissors, and Sanchez goes first. And so he gets to his pick of 12 offices. But after he's chosen, then Patel would go next, and he would have 11 offices to choose from because Sanchez will have gone first. And so as you can see, the answer is very straightforward. There's in 1 ways, where in 1 is 12 for Sanchez to choose, and in 2 ways, where in 2 is Patel. for him to choose his office. And so there's n1 times n2, or 12 times 11, or 132 ways to assign the two of them to an office. So if and we can see how we can construct a little bit more. So first of all, this should be very apparent. It should be somewhat intuitive off the bat, and if it's not, then it's the type of fundamental rule that we can use to build more advanced theorems and concepts off of. And just hinting towards that, you can kind of see how we're branching towards combinatorics already, right? So there were 12 offices, and the number available for each successive action, where the action is the assignment of an office, has to deal with the number of remaining offices available after that first one, right? So if you're drawing out of a hat, or if you're just allowing them to select, it's the same, but the idea is that you choose exactly one office per person. And if there were 12 offices and 12 employees, there would be 12 factorial ways to assign those offices to those 12 employees. But when there are fewer employees than offices, then it's very similar, but we use the product rule, and we continue to apply it. So if we had a third employee, Claire, then whenever her assignment came, or whenever her choice came, there would be n3 equal to 10 remaining offices for her to choose after Sanchez and Patel had already been assigned. And that would be n1 times n2 times n3, and so forth. And we can see how this is following the pattern of a factorial, and n4 would be 9 available offices, and so forth. And so you can see that it has this form, n factorial over n minus k factorial, where n is the number of offices and k is the number of employees. Or if you were to think of lottery numbers, then n would be the number of ping pong balls, and k would be the number of times that you've drawn the ball out. And that'll give you the number of distinct assignments, where it's a little easier to think of offices in terms of this rather than the lottery, because in the lottery the order doesn't matter. But let's say that we did want to consider the lottery. So this formula doesn't quite work, right? Well, not yet. But if we remove all of the repeated, so in that case, we're not interested in who gets which office. We're interested in which offices have already been consumed or assigned or whatever. So we're not looking for the ordering or the specific assignment to an individual or a place in line or whatever. We're looking for the number of offices or the number of combinations that result in equivalent selection, right? So in that case, we would remove each of the k factorial permutations, or different arrangements of the same set of, in this case, 3 offices, right? So if offices 101, 102, and 103 are all taken, and we only care, which ones are remaining, then we don't care who sits in office 101, 102, or 103, whether it's Claire, Patel, or Sanchez. We just care that those offices are taken. And so there's k factorial permutations or rearrangements, or reassignments of those same 3 offices to the same 3 people. So we divide that out, and we get a very familiar formula. We get n choose k. We get n factorial over k factorial times n minus k factorial. And so I just thought that was really cool, that already you can see how this simple rule that probably a few minutes ago didn't seem like it was really worth paying attention to, the product rule, constructs something that's extremely fundamental in the study of statistics. And anyway, so I just thought that was interesting. Okay, so the sum rule, whenever we had mentioned again, that and is product, and or is addition or sum, this is the application of that in terms of sets. So this one says that if a task can be done in one of n1 ways or n2 ways, where none of the set of n1 is the same as the set of n2, then there are n1 plus n2 ways to do that. And so I think that one's a little more easily understood in terms of an example. So let's say that you have to choose the someone to represent the school, and so that choice would either come from the faculty or the students. And so in this example, we say that there is 37 members of the faculty and 83 members of the student body. So if it has to come from one or the other, then it comes from one of the sum of those two groups, right? Because we are assuming that no one is both a faculty member and a student. And so the solution breaks down pretty quickly, right? N1 is the number of faculty, 37. N2 is the number of students, 83. And so you're choosing from a pool of 120 possible representatives, right? So that's when you would apply the sum rule. And so the subtraction rule is really a compound or something, a rule bolted on to the addition rule, but it's going to be a fundamental importance whenever you're trying to determine the size of a set. So if you'll remember, I said that the difference between a set and an array, or some other concept, is that a set applies a guarantee of uniqueness for its elements, and so whenever you're unioning two sets, you're not guaranteed. You're guaranteed that the result has distinct elements, but you're not guaranteed that those two base sets, the ones that you're merging together, are distinct. So if you consider the example we just spoke about, where you're choosing from students and faculty, if there was an individual that was both a student and a faculty member, then they would have been repeated in the head count. And so in order to make it fair, where no one gets two votes basically, or two chances to be selected as the representative, then you would add the sets together, and then you would subtract the people that had been counted more than once. In that case, it would be the individuals that are both faculty and students. And so that's exactly the concept of the subtraction rule. And so it says if there's, again, it starts the same. If there's n1 ways or n2 ways, then it's n1 plus n2 minus the number of ways that are common to both, so minus the intersection. And so this is the concept of the principle of inclusion and exclusion, and whenever you go on to discrete math 2, you'll go into that in a little more detail. And so it's the principle of inclusion and exclusion applied to two sets. And once you start applying it to more than two sets, then you have to start considering the intersections of all combinations of sets. That the construction of that is a little bit larger. And so I have a more complicated example, but I wasn't able to prepare it in time. So we'll look at an example from the book. And so this one discusses the number of bytes that begin. So a byte is a bit string of length 8. Right? And so the number of bytes that begin with a 1 and end with consecutive zeros. And so you can already think that these two sets aren't necessarily exclusive of each other. So if you fix the first bit to 1 and then you allow the other 7 bits to vary, several of them are going to end with consecutive zeros. In fact, if you were to just count, then the very first one you consider would have consecutive zeros. And likewise, just because it ends in 2 zeros doesn't mean the most significant bit can't be a 1. So then, how do we answer this question? Using our newfound rule. And so first, we break it down, and so we're really considering two sets here. We're considering set A, where the first bit, the most significant bit, A7, is set to 1, and then the other bits are allowed to vary. And then we're considering set B, where where the least significant bits, B1 and B0, are both 0. And then we compute the size of those two sets. So with 7 degrees of freedom, there's 128 bytes that in which the most significant bit is set to 1. And then there are 64 bytes in which the two least significant bits remain unset or are assigned the value of 0. And then there's the intersection, C, which is equal to A intersect B. And that one only has 5 degrees of freedom. So when counting the intersection, the most significant bit, C7, is set to a 1. So there's no variance there, so it doesn't factor in. There's only one possible way to represent it when it's fixed. And then, so we are still applying the product rule. We're just multiplying by 1, so we leave it off. And then again, we're fixing the two least significant bits. And there's only one way to set them to 0, or to assign them the value of 0, or to leave them unset. And that is to assign them the value of 0. And so again, we're multiplying by the product rule of 1, since there's only one way to do that. So we just leave that off of our calculation. And so now there's 2 to the 5, or 32 ways in which the first bit is set and the least significant bits, the least significant 2 bits, are unset. And so using our rule, we add together the size of our first set to the size of our second set, and we subtract the ways to satisfy this proposition, which are common to both. So it's 128 plus 64, so the size of set A plus the size of set B, minus the size of their intersection. And so we end up with a total of 160 distinct bytes in which either the first bit is set or the two least significant bits are set. And so again, it's the addition rule, but where it's cleaned up so that we're only considering distinct solutions. And so that is the subtraction rule. Okay, cool. So we will finish up chapter 6 on Monday, and then we'll have our bonus lecture next Wednesday. The homework I assigned today will be the last one, and then next Wednesday I will post the exam review, and then on Monday the 27th I will go over the exam review, and then on Wednesday the 29th you'll have your third and final exam, and then you will be free of discrete math. So okay, email me if you have any questions. Otherwise, look for the homework to be posted a little later today. All right, thanks. Bye.